Welcome everyone to this lecture on an introduction to the perceptron. Before we launch straight into neural networks, we need to understand the individual components first, such as a single neuron. Artificial neural networks, or ANNs, actually have a basis in biology. So we're going to see how we can attempt to mimic biological neurons with an artificial neuron, otherwise known as a perceptron. And then once we go through the process of how a simple perceptron works, we'll go ahead and show you how you can represent that mathematically. But let's start off with a biological neuron, such as a brain cell. So a biological neuron works as in a simplified way through the following manner. Basically, you have dendrites that feed into the body of this cell. You can have many dendrites. And what happens is an electrical signal gets passed through these dendrites to the body of the cell, and then later on, a single output or a single electrical signal is passed on through an axon to later on connect to some other neuron. And that's the basic idea. We have kind of these many input of electrical signals through the dendrites, goes into the body, and then a single electrical signal output through the axon. So the artificial neuron also has inputs and outputs. So we're going to attempt to mimic the biological neuron. So this simple model again is just known as a perceptron. And in this case we have two inputs. So let's go ahead and see a simple example of how it can work. So we have two inputs and a single output, and we start indexing at 0, so we have input of 0 and input 1. So the inputs can have values of features. So when you have your data set, you're going to have various features, and these features can be anything from how many rooms a house has, or how dark an image is, represented by some sort of pixel amount or some sort of darkness number, etc. So essentially, don't worry right now about what these numbers actually represent. Later on, when we're dealing with real data sets, we'll have something more tangible. For right now, these are just arbitrary number choices. But again, we have input 0 and input 1. So again, indexing starts at 0 here, and we're going to assign them values of, let's say, 12 and 4. Then the next step is to have these inputs multiplied by some sort of weight. So we have weight 0 for input 0 and weight 1 for input 1. And typically the weights are actually initialized through some sort of random generation. So you just choose a random number for these weights. In this case, we'll just go ahead and pretend that the random numbers chosen was 0.5 and -1. Again, the numbers here are pretty much arbitrary. Really focus on the general process. So now these inputs are going to be multiplied by the weights. So that ends up looking like this. We have 12 times 0.5, or 1/2, and that equals 6. And then we say 4 times -1 is equal to -4. The next step is to take these results of the inputs multiplied by their respective weights and pass them into an activation function. There's many activation functions to choose from, and we're going to cover this in a lot more detail later on. For now, our activation function is actually going to be very simple. We're merely going to say the following. If the sum of the inputs is positive, return 1, or output 1. If the sum of the inputs is negative, then output 0. So in our case, if we say 6 plus -4, that's the same thing as saying 6 minus 4, so then we get 2 as the result. So since the sum of the inputs was positive, the activation function returns 1 or outputs 1. So there's a possible issue here, and the issue is the following. What if the original inputs started off as 0? Then any weight you chose, even if it was randomly chosen, multiplied by the input, would still result in 0. So if input 0 happened to be 0, and input 1 happened to be 0 as well, instead of 12 and 4, then you could have a problem. You essentially always get out 0 because 0 multiplied by any weight is still going to be 0. So we can actually fix this by adding in a bias term, and in this case we choose 1. So we're going to go ahead and add in our own bias term, here plus 1. So what does this actually look like mathematically? Now let's quickly think about how we can represent this perceptron model mathematically, and it's actually quite simple. Basically, we just say the following. From I equals 0 to n, that is the number of inputs, we're going to say w of I, or that specific weight for that input, multiplied by x of I, which is the input itself, plus the bias term, and that's essentially it. So once we have many perceptrons in a network, we'll see how we can easily extend this to a matrix form. So as a quick review, in this pretty simple lecture, we just covered briefly the following. We discussed in the very basic terms how a biological neuron works, then how that can reflect to a perceptron model, which is the artificial neuron, and then the mathematical representation of that perceptron model. Coming up next, we're going to continue discussing how we can build off this perceptron model to build a neural network. Thanks, and I'll see you at the next lecture.